Welcome to ChemDoctor, and this is the very first presentation on energy. So, energy in chemical systems. All right, so chemical systems, and I'm going to define this two ways. A chemical system can be a physical change or transition. All right, and probably, the easiest example of this is the melting of ice, right? That's a physical transition or a physical change because we're going from the solid material to the liquid. And there's no alteration in the chemical component of water itself, right? This would be H2O as the solid being melted to H2O, the liquid, and there's no alteration in the chemical composition of the liquid, right? And the other thing that a system can be is a chemical reaction. All right, and I'm going to abbreviate reaction as RXN. And remember, with chemical reactions, that we have bonds that are breaking. So bonds broken. And we also have bonds forming. And in that transition, we can have the exchange of energy, right? When we have a physical change, we can have the change in energy. To go from ice to the liquid, common sense dictates that you're going to have to warm the material up. You're going to have to heat it up. In a chemical reaction, you're going from the reactants to the products, just to simplify this. And depending on the types of bonds that are being broken, and then the types of bonds that are being reformed, you can actually have energy that is either exiting or entering the system. And we're going to talk more about that in a minute. Now, both of these possibilities involve the change in energy. Change in energy, and I'm just going to abbreviate that as E. So let's talk about basically the types of energy. All right, so I'm going to move this over here, and we can break down energy in chemistry to two types. We have predominantly kinetic energy, and we have potential energy. Now, over the year, you guys have heard me talk about kinetic energy often. And I don't know, at this point in the year, you should be able to do what I'm about to do here, but we'll see what happens. So kinetic energy, another way to look at this is thermal energy. Remember that kinetic energy, so kinetic and thermal energy are one and the same. And both of them talk about motion, right? The particles are moving. Remember that particles have two kinds of motion that are possible. One type is vibrational. So vibration. So for example, if we have a water molecule, and you should be comfortable with the loose formula, the two oxygens are bonded by a double bond. And when we're talking about vibrational energy, the bond can shorten. Whoops, I wanted a different color there. When we talk about vibration, the bond can lengthen and it can shorten. And you can imagine other things that the molecule could be doing too. The oxygens could be twisting relative to one another and so on. Those would all be vibrational types of motion. And then the other type of motion we can have in chemical systems relative to kinetic energy is going to be translation. And the easiest way to understand that is just to think about a baseball. If you pick up a baseball and you throw it across the room, you've translated the ball from point A to point B. So it would be taking an object literally. And if this is point A, and you move it to point B. All right, so molecules and systems can have these two kinds of energy. And when it comes to kinetic energy, right now we're talking about kinetic energy. So the kinetic energy is composed of movement, and you can boil the movement down into two types: vibrational or translational. And we've talked about this stuff before. When you consider a solid, right, the only kinetic that it has is going to be vibrational. I'm just going to abbreviate that. Both liquids, though, and gases can undergo translation. And they're also doing vibrational, right? Don't break this down into some black and white thing. In liquids and gases, you have translation going on. But since a gas can be composed, like if we're talking about air, and there's N2 in there, and there's O2, both of these molecules have internal vibrations, which I just described over here. So the point is, with the liquids and the gases, that you've got both kinds of kinetic energy going on, the vibrations and the translation. The solids, though, are basically vibrational, and that's what it is. Now, when we talk about potential energy, actually, let me see if I can do this really quick. No, I can't. So what I'm going to do is I'm going to squeeze this in down here, right? I want to change the color. We'll go to red. All right, so potential energy. Potential energy. All right, so we can basically have, or at least we're going to simplify this down into two types. We can have location, right? And you guys are familiar with that because I've been drawing pictures all year long with rocks on top of cliffs. I can put one right here, all right? So we have this cliff. Here's the rock at the top. This is a potential energy difference based on its location. However, in chemistry, quite often, in fact, even most of the time, we're talking about a form of potential energy that's called composition. And what this is about are the types of chemical bonds that compose the things that are interacting. So this would be the types. We can simplify this. We'll say this is the types of bonding. And to give you a really quick example, change the color here. If we look at the reaction between oxygen gas and hydrogen gas, there should be a 2 in front of this, right? So let me just do that. To make water, all right, here we have a definite potential energy difference between the reactants in this reaction and the products. The two reactants here, the H2O and the H2, have high potential energy. You can it's okay to consider or think about this as being, these two reactants are sitting at the top of a cliff. But the top of that cliff doesn't have to do with the location, right? It's not a physical location. What it has to do is with the types of bonds that they have, all right? And the H2O, which is what the O2 and the H2 become, have a lower potential energy. And when this reaction occurs, so let's say that we had a mixture of oxygen and hydrogen in a bottle, right? And then you were to light a match and put it in there. Well, what's going to happen is you're going to see a bright flash and there's going to be a loud bang, right? And that is literally those two components coming together, we have the bonds that make the oxygen breaking, the bonds that make the hydrogen breaking, and then we have the reformation. And when the reformation happens, there is so much energy released going to the H2O. All right, that's where all the light and the heat comes from, right? This is when you ignite oxygen and hydrogen together, that produces energy. And where that energy is coming from, it's being released from the where it was stored in the oxygen and the hydrogen bonds. And now when you produce the H2O, the bonds between the H and the O and the H2O are at lower potential energy. And the difference in energy is the energy that the human perceives, the flash when you stick the match inside the bottle. If you were hanging onto the bottle, which actually wouldn't be too smart, you'd feel it warm up. That's the energy being released from that particular reaction. All right. So I am now going to conclude this video, and the intention of this video was to define the various kinds of energy for us, the concept of kinetic and potential energy, the fact that kinetic energy and thermal energy and motion are all strongly related, the fact that potential energy can be a location issue or a composition issue, where composition happens to be the types of bonds between atoms, and it can be the types of bonds between molecules. So this is ChemDoctor signing off.